Okay, so this is the last sample problem of chapter 25. So it says a parallel plate capacitor of plate area A and plate separation D. A potential difference V0 is applied between the plates. Okay, so actually we try to provide we try to provide a V0 here. Okay, try to provide a V0. And then the battery is then disconnected. Okay, so we only charge it to V0. Okay, so after we charging it, then we try to remove the battery. So this is V0, this is 0 volt. Okay. And then a dielectric slab of thickness B and dielectric constant copper is placed between the plates, assuming AD, V0, B, and copper. Okay, what is the capacitance C0 before the dielectric step is inserted? Okay, so this is the initial case without this slab yet. Okay, so this will be easy because we just need to calculate C0 as epsilon naught. Epsilon naught is like the vacuum. And then times A over D, because we have all these variables. So epsilon naught is 8.85 times 10 to minus 12, and then times A. This is centimeter square. So we need to convert it to meter square for the SI unit. So this is like 10 to minus 4. 10 to minus 4, because 1 meter is 100 centimeter. So 1 centimeter is 0.01 meter. So 10 to minus 2 or 10 to minus second power, so square, so 10 to minus 4. And then over D is this one, 0.0124. Okay, so C0 is 8.21 times 10 to minus 12 farad. Okay, so this is the answer. Or usually I will use the scientific prefix, so it is like 8.21 picofarad. Okay, both of them are okay. Okay, so this one is easy. So for question A, we don't consider any dielectric yet, so we just need to plug in the variable to the capacitance for a parallel plate capacitor, which is like a C equals epsilon naught times A over D. Okay, so for the next one, what free charge appears on the plate? What free charge appears on the plate? Okay, so it is also very easy. Yeah, so here we still don't consider the dielectric yet. So we just need to use Q0 equals Z0 V0, okay, to get the free charge, or maybe just denote it as Q, because on the figure it is just Q, not Q0. So, but this is a minor problem. Even though you write it as a Q0, it's okay. Okay, so in the previous question, we already know that C0 is 8.21 times 10 to minus 12. And then V0 is given here, 85.5 volt. Okay, so this is 7.02 times 10 to minus 10th coulomb. Okay, so this is also easy. We already know the capacitance and the potential difference. Then we can calculate the charge. Okay, so next, what is the electric field E0 in the gap between the plate and the dielectric slab? Okay, so here we try to consider, we already have the dielectric slab, but this slab is thinner than the distance between the two conducting plate. Okay, so this B is only 0.78 centimeter, okay, for B. And then for D is 1.24 centimeter. So there will be gap between the slab and the plate. Okay, maybe this one move higher or lower, but it doesn't really matter. You can actually put this one touching the top plate or touching the bottom plate or at the middle. It doesn't really matter. So at this, considering this case, the slab is placed in the middle, so there is a gap on top of it and then at the bottom of it. So yeah, so in this case there will be this one will be E0. This one will be E0. And then in the slab there will be another E. I'm not sure what is the notation, but for this question C, we would like to consider E0 first, which means the E field between the slab and the conducting plate. Okay, so this is nothing special. We will try to use the Gauss law to calculate the E field, E sub 0. And here we will consider the Gauss surface 1. And Gaussian surface 2 will be used later to calculate the E field inside the slab. So here we consider the Gaussian surface 1 first. Okay, so in this case, as much as this is the vacuum, so we use the original Gauss law, epsilon naught times integration of E dot dA and then Q enclosed. So Q enclosed. So for this one, Q enclosed is nothing but plus Q. So this is actually Q. Or maybe here I just write it as Q0. So yeah. So actually this is Q rather than Q0, so that it matches the notation on the figure. Okay. But yeah. Okay. So here we try to evaluate the surface integral, integration of E dot dA. So for this one, for the top surface, it shouldn't contribute anything because the E field inside the conductor should be 0. And then for this one, 0, this one 0 as what we have mentioned before. So the only surface contribute to the net flux is the bottom surface. So for the bottom surface, the E0 is pointing downward, which means pointing outside. You can consider dA is pointing downward. So E0 and dA are pointing to the same direction, which means that this is nothing but epsilon naught EA equals Q. Or maybe we can write it as E0 because E0 is the E field between the conducting plate and the slab. Okay, so we denote it as E0. Okay, so in this case, we can actually calculate E0, which is Q over epsilon naught times A. So in this case, Q is 702 times 10 to minus 12, and then over 8.85 times 10 to the negative 12, and then times A is this one, 115 times 10 to the negative 4th. Okay, so this number is 6,900 volt per meter. Okay, this number. Okay, so this is so this is not difficult. We just try to apply the Gauss law for the Gaussian surface 1. So maybe I can just put a 1 there, so that to remind you, that is for the we use the Gauss law for the Gaussian surface 1. But even though you don't write 1 there, it's okay. But of course, if you really write, then it will be more clear that you try to apply the Gauss law for this Gaussian surface rather than that one. Okay, so next for question D, what is the E field E1? Okay, so this is E1. This is E1, this is E0, this is E0. Okay, so what is electric field E1 in the dielectric slab? Okay, so here we try to apply the Gauss law for this Gaussian surface. Gaussian surface. Okay, so this one is like here. So it includes a surface in the vacuum. Okay, so for this one, this side won't contribute the net flux. Only this side will contribute the net flux. Maybe you will ask whether we can make the Gaussian surface 2 to be like this, fully symmetric to that one. I'll say yes, you can redo so, but I think why so I mean like this. So this side is inside the conductor. I would say yes, but the idea is that because he tried to draw Gaussian surface 1 and Gaussian surface 2 in the same diagram. So if he just define Gaussian surface 2 to be like this, and this Gaussian surface and this Gaussian surface will overlap. So yeah, then you may wonder, or what is Gaussian surface 1. So to make it to make it totally symmetric, okay, so it try to define the Gaussian surface like this, and actually the equation on both sides will just have one additional minus sign, and then they finally cancel, so you will get the same result. So here we try to apply the Gaussian surface for this one, for Gaussian surface 2. So for Gaussian surface 2, we try to apply Gauss law, but yeah, this is not the original Gauss law, because this surface contribute to the net flux is inside the dielectric, which means that we need to consider the kappa here. So we have kappa E dot dA equals Q enclosed. So here for the Q enclosed, it enclosed this one. Okay, although it mentioned that there are some plus Q prime, negative Q prime here, we don't try to consider that as the free electron. So in the textbook or in the slides, some sentence has mentioned that we don't really consider this kind of charges inside the dielectric to be the Q enclosed. So here the Q enclosed is only negative Q. So this is negative Q. So we have negative Q here. Okay. Another reason is that this kind of charge has already been considered as the kappa K. So if you have kappa K here and still consider the Q prime, then you will consider it doubly. Then it will be a mistake. So we consider the dielectric as the kappa, and then on the other side we just consider the excess charge, the free charge. So we only consider these charges in the conductor. Okay, so here we try to explain it. So this is like this is E1, and then if you consider dA pointing outward, okay, dA should be pointing upward for the top surface, which means that E1 and dA points to the opposite direction. Then there will be a minus sign. So it is like minus epsilon naught kappa E1 and then times A equals negative Q. So finally we will have a negative sign on both sides, and then they turns out to be cancelled. If you just define Gaussian surface 2 to be like this, then both of them will be positive, and then the result will be the same. So here we can have E1 to be Q0 over epsilon naught kappa A. Okay, so it's like 702 times 10 to minus 10 over 8.85 times 10 to minus 12, and then times kappa. Kappa is here 2.61, and then times A, still this A, 115 times 10 to negative 4. Okay, so this number is smaller by this factor. Okay, so this is 2640 volt per meter. 2640 volt per meter. Okay, so this is, yeah, here the same thing. Okay, so here we come to the part E. So it asks, what is the potential difference V between the plate after the slab has been introduced? Potential difference V. Okay, originally we try to charge the capacitor without the step with the potential V0, and then this is 0 volt, like this. So after plug in the slab, and then of course the battery is removed, so there is no way for the charge to go, which means that the C has already changed. The C has already changed, and then Q doesn't change. Q doesn't change, which means that the voltage or the potential difference should change. This one does not change, which means that yeah. So here the V should have changed. So in that case, we try to calculate the new potential difference between this plate and this plate. Okay. So here, let's call it V. V will be integration of E ds from negative to positive. Okay, from negative to positive, which means that the path is from here to there. This is the path. Okay, so here, so just as what I mentioned, this is E0, this is E0, and then this is E1. Okay, so as much as inside, for example, this is part 1, this is part 3. Okay, for part 1 and part 3, the E field are uniform and has the pointing to the same direction and has the same magnitude as E0. Okay, so if you consider the potential difference for this part and this part together, then it should be E0 times D minus B. D minus B. D is the total length, and then B is the thickness of the slab. Okay, so you don't need to consider how thick is this one, how thick is that one. As much as when they add together, they must be D minus B. So this is the total potential difference for part 1 and part 3. Okay, so this is for part 1 and part 3. And then the remaining one is the part 2. Part 2 is plus E1 times B. Okay, so we just need to plug in the number because we already calculate E0, E1, and then we also have D and B. So we just need to plug in the number. Okay, so E0 is 6900, and then times D minus B. D is 1.24 minus 0.78 times 10 to minus 2, and then plus E1 is 2640 times 0.0078. Okay, 0.0078. Okay, correct. Okay, so here we have V to be 52.3 volt. 52.3 volt. Okay, originally V0 is 85.5 volt. Okay, so V becomes smaller, and we can simply consider as much as Q doesn't change, and after inserting the step, C must be larger. C must be larger, which means that we have a Q equals CV, which means V equals Q over C. Okay, this one doesn't change, this one become larger, so V must be smaller. So this makes sense. If you just calculate V to be a larger number than V0, then it must be wrong. At least we know this might be correct. Okay, so this is for part E. And then for part F, so it asks what is the capacitance with the step in place between the plate of the capacitor. So after inserting the step, what is the capacitance? What is the capacitance? So C is Q over V. Q over V. Q doesn't change at all from start to the from beginning to the end. So this is 702 times 10 to minus 12, and then over. Just now V is 52.3. So this is 52.3. Okay, so C becomes 13.4 picofarad. 13.4 picofarad. Originally the capacitance is how large? Originally the capacitance is Z0 is 8.21 picofarad. Okay, so you can consider like for the whole one, this is still 8.21 picofarad, but for this thickness, it becomes 2.61 times larger. So yeah, by this kind of simulation, numerical values, then you maybe also calculate the total capacitance becomes larger, but yeah, not really 2.6 times 61 times larger, because yeah, for this part and this part, yeah, it is still vacuum, so the capacitance for this part and this part doesn't change. The 2.61 times only apply to the thickness of B. So this is B 0.7A, this is 1.2, slightly more than a half. So it only increase for like 60 or 70% of the capacitance. Okay.